that somebody pointed out on either by emailing me or on the discussions board that my answers on the previous review session were different on this first question about data types. And that's never good, right? I normally don't look at the answer sheets because I figure, doing this long enough that I should know the answers. But occasionally there's, especially on these data types, occasionally there's a little bit of a difference in opinion. So I'm going to go over those quickly so we get those straight. Okay, occupation. Now, I'm going to, excuse me, I may use some different descriptors for data types occasionally because some of the software we use describes data types, some kind of data types, a little bit differently. For instance, numerical variables like blood pressure, height, BMI, and so on and so forth. That's a continuous variable. It's a numerical. You might call it a numerical variable. You might call it a continuous variable. SPSS calls them, wait, let me think for a second. Let's see what they call it. They call it a, let me see, I'll open up SPSS. And we'll take a look at it. But we're referring to the same kind of variable, something that's a continuous number scale. And in fact, there are only three choices in SPSS in terms of how you're going to be handling data. Let's see, so the variable view, and let's look at only giving me two there. I better put a number in there or something. Nominal. In other words, nominal it's using for numerical or for in what we've described here as continuous. So continuous, numerical, scalar, or excuse me, scale. It uses the term scale rather. Continuous, numerical. Let me start again. There are times that the words we use to describe variables may vary a bit depending on what software we're using, what we've grown accustomed to, and so on. Now, but the categories really are three basic categories. For instance, in SPSS, they describe a number that's on a number scale, blood pressure, BMI, pH, so on and so forth, as a scalar variable, a number that's on a scale. Could be 0 to 100, could be 50 to 5,000, and so on and so forth, but it's a number on a scale. They describe data that has a name, like, for instance, left-handed or right-handed, or male or female. They describe that as nominal data in SPSS. Now, there's a special category of nominal data where it's a name, but the name has order. For instance, poor, fair, good, excellent, right? Those are names. They're not numbers, they're names, but they clearly have an order. That one is better than the other. Okay, that's called, that is a categorical variable, a nominal variable or categorical variable. That's called, and more properly called, an ordinal variable, because it not only does have the property of having a name, like a nominal variable, but it also has this order that we can identify. Pain scale is a typical example of that, right? How much pain are you in? Well, from 1 to 10. Well, if somebody says to you 7, that tells you a level. That's not really a number 7 that you can use usefully, but it tells you that for them, that's the level of pain that they're in. Now, their 7 may be different than someone else's 7, right? And the difference between a level of 2 and 4 and between 7 and 9, even though it's two numbers, the difference may not be the same. We have no way of measuring that. But it's clear that those categories, 1 through 10, 0 through 10, it's clear that those categories have some order. So a better way of describing that, even though they're nominal variables, they're names rather than numbers, really names rather than numbers, a better way of describing them is ordinal. And in fact, there are reasons for doing that statistically, as we'll come across later on. So those are the three that we use there. But, there's some others that come up as well. For instance, when we talk about numbers, very frequently when we're talking about small numbers that are integers, for instance, the number of siblings that you might have, right? Now that is a number, that's a number scale, 0 to, I don't know, biggest family might be 15 or 20 or something like that. That's a number. However, it's an integer. It's always going to be an integer. It's always going to be a discrete value that has an integer value. So even though that's a number or a numerical variable, it has a special name that we call discrete numerical or just discrete. We call it discrete numerical or just discrete, right? So sometimes I might, for instance, say population size, number of people. If the population size of New York State is 5,300,000, probably more than that, probably 12,300,042 people, right? I might just call that a numerical variable, or I might call it a discrete numerical variable. In fact, in this particular example, our answer sheet calls it a discrete numerical variable. So I guess based on what our answers are here, I'd probably say that you could probably use either one, but discrete would probably be the better answer here if it's offered. Similarly, community size, rural, small town, small city, large city, those are names, right? So they are categorical variables, right? Or sometimes called nominal variables, like in SPSS. They are categorical variables, but a better answer would be ordinal because they're that kind of special variable. Okay, so occupation, categorical, social status, ordinal, right? Categorical, but really ordinal is a better description. State murder rate, that might be 323.3 per 100,000. I would call that a continuous variable, right? It's not necessarily an integer. County population size, the number of people living in the county, that's a number, right? However, it's going to be an integer, so it's going to be a whole number. So you could call that a numerical variable or numerical or scalar variable in SPSS, or you can call it a discrete variable as well because it is an integer. Population growth in percentages, right? That we have that here. Population, that's a continuous or a scalar or again a numerical variable. Okay, in this example, we're sticking with the terms categorical, right? Continuous and ordinal and discrete. So probably on the test, we'll probably stick with those also. And we can always make adjustments if there's some confusion on the test. So I wouldn't panic on this stuff too much. Okay, but just make sure you know the basics of this. Community size, again, we already talked about that. It's categorical, but more properly described as ordinal because it does have order. Annual income, that could be, $30,523. That's a continuous scale pretty clearly. And attitude, so there's affirmative action, favorable, neutral, unfavorable. Those are categories. But again, let's see. You might call that ordinal. You want to know something? That's probably the one that the person was most concerned about because they suggest a difference, a rating or a difference, but I'm not so sure that you can really say that there's order when you talk about favorable, neutral, or unfavorable, unless you look at it in the light of you're trying to demonstrate that favorable ratings are increasing or something like that. So this one's a little bit trickier, right? But I think categorical or ordinal would be a good description either way. Scalar meaningful numbers regardless of what. Yeah, scalar for as far as SPS is concerned, anything that's a number scale is going to be called scalar, whether it's discrete or continuous. It's going to be called scalar as far as SPSS is concerned. And nominal is going to be any categories that don't have order, built-in order, like gender or hair color or something like that. And ordinal is going to be categorical variables, nominal variables that have some sort of innate order that we can identify, but are not on a number scale, right? That are not described by numbers where you can describe how much more one is than the other than just that it's more. Okay, so I think we beat that to death, right? Okay, so I hope that clarified thing. And you want to know something? I guess maybe he was referring to number 8, because I might have suggested that. Gee, I don't think that's really ordinal, because you'd have to make a judgment call, one better than the other or one different than the other, rather than just saying that the values are different than the other. Okay, so the next thing I wanted to bring up was I wanted to go over the homework problems also. But before that, I had a couple of questions. I want to go over at least one example of empirical formula and the z, using the empirical formula and the z table, and at least one example of binomial distribution, because that brought up some questions based on the last review as well. So let me see if we have an additional. Maybe I'll just make them up in my head, or you know what's even better, maybe let me go to the homework. Let's review the homework, because we had some examples in there. Well, a scalar always has order, right? In other words, if it's a number, it always has order. If one value is 110, the other value is, 112. We know that it's 2 more than the previous value. And the difference between, let's say, if we're counting beans, right? The difference between 100 beans and 102 beans is the same as the difference between 40 beans and 42 beans. Oops, I opened the wrong one. By the way, guys, if you, I have you muted, so that's to avoid some crosstalk and stuff like that. But since there's only 2 of you, you can either type questions into the chat box, or you can, if you want, you can ask me to turn your mic on and you can actually speak. If you have, it looks like you guys have mics on your computer from what I can tell from here. Okay, let's go into assignments. And let's take a look. Yeah, let's go. I just want to skim through them so that we can see what's going on here. I'll begin. So actually see in the exam. I'll be out a bit. Okay, so what do we have here? Question 1, we go through the various possible scenarios in terms of the types of variables. And in this one, which of the following are categorical variables? I give you a key in here that there's 2 correct answers here. So categorical variables, I guess, what's your country of origin? Siblings, that would be, what would that be? That would be a discrete numerical variable, right? It's a numerical, but it's discrete. Do you smoke? That's a yes or no, right? That's a categorical variable. How many cups of coffee did you drink this week? Well, if we're talking about whole cups of coffee, that's a discrete numerical variable. If I ask you, what's the average number of cups of coffee that you drink per week? It might be, if you kept track of it all week, it might be 17.4. So now that, instead of being a discrete numerical variable, that's a continuous variable. What's your blood pressure? Continuous variable. Even though it might be an integer, in other words, you go to the doctor, your blood pressure is 120/80. That's millimeters of mercury pressure that you're describing there. So even though they may write down 120/80, well, your real blood pressure might be really 120.113 over 80.17 or something like that. So it's really, even though they write it down as an integer, it's really a continuous variable. How would you rate the MPH program? Excellent, good, fair, poor. That's a categorical variable again, but it's a special form of it. right? Special form categorical variable, which is called ordinal. So we would, better description of that would be an ordinal variable. So you can expect to see something like that. You can expect to see something like a description of a histogram where you're asked to make various calculations. The key here is the recognizing that the y-axis here is the frequency or the number of people that fall into the category that's described in the x-axis, right? So in other words, how many people are age 20 to 29 among this among this sample of people, lottery winners, right? We can see that there are 2 people that are in that age group. If we wanted to know how many people were here altogether, we could just simply add up. There's 2 people, there's 5 people, 7, 6 is 13, and 8 is 21, and 5 is 26, and 4 is 30. So there's 30 people that are here described in this histogram, right? And if I asked you what percentage of people that won the lottery were under 30, you'd say 2 out of 30 or 2 over 30, and give me whatever that percentage was, right? Or proportion was, like probably that would probably be about I guess 0.6, 0.7, 0.06, 0.07 or something like that, 6 or 7%. I would consider giving answers as proportions rather than percentages, unless you're giving specific guidelines. Most likely on the test you'll be giving specific guidelines as to whether to describe it as a percentage or a proportion. Okay. Based on the histogram. Now, if you do it wrong, I mean, you can always go back and fix that, but it's better if you get it, follow the description that the problem's looking for. It'll be less likely that if there's a certain portion of the test that's auto graded, that it'll get it wrong. But we always go back and kind of check those things anyway. Based on histogram alone, what's the probability randomly select the lottery would be 60 or older? Well, you got 5 people, 4 people, 10 out of 30, about 33% or 0.33. Okay, now you might also get something in here that's we'll sneak in a little bit of a conditional probability. For instance, based on histogram above, given a lottery winner is known to be younger than 60, what's the probability that he's also younger than 30? So in that case, we're only looking at people that are younger than 60, and there are only 20 of them, right? What's the probability that they're younger than 30? Well, there's 2 of them. So out of the 20 that satisfy that condition, only 2 of them are actually younger, right? So 2 out of 20 would be 10% or 0.1. So yeah, so you'll see some problems like that. I'm not sure there'll be anything on SPSS, although there may be things that you can use the function in Excel or use SPSS on computers there to do certain calculations. Like, for instance, you might be asked to, given a data set, and asked to calculate the mean, the median, the interquartile range, and so on and so forth. If you're familiar with SPSS and you're asked to do that, you can do that in no time at all. You can also do it in Excel, just a little bit more effort, right? So we've done, if you go back over the videos, the lab videos from the first 2 sessions that we had, that should help you out a bit in terms of calculating descriptive statistics. Okay, so let me go on to the next homework. So after this, I don't want to close the window. I want to leave the page. Okay, yes. Okay, our nemesis, Venn diagrams. Okay, so here's our Venn diagrams. You probably have already started talking about this. The key here to keep in mind is that this straight up U means union. In other words, the union of 2 different possibilities or 2 groups. In other words, another way of looking at that is an either or kind of situation. In other words, A and B both satisfy this condition, right? So if I looked over here, the one that most likely looks like that is this one over here. So A or B, A or B, either one, doesn't have to be both, but either one satisfy that condition. That's called union. Okay, this upside down U represents intersection, right? So an intersection, it means it has to be both of them, right? So I'm going to look at this one down here first. A intersection B means it has to satisfy both conditions A and B. Well, what do we have here? Well, look at this one over here, this grayed out area here. That satisfies both A and B, and everything, just A alone is not satisfied, just B alone is not satisfied. So we would have that situation. Now, just B, well, B, it would just be B, right? We have that, and A would be just A, right? Here we go. And with no relevance to whether it includes B or not, just means that if a person satisfies B, like A might be has heart disease, B might be has cancer. So you might have some people that have both, but they're not concerned about that there. If they have cancer, then they're all part of that group A. Okay, so we've gotten through those two. Well, how about this one here? That gets a little funkier. It's the intersection of A with, and those got to satisfy both conditions, A, and that little tick mark on B, that little apostrophe on B, represents not. A intersection not B means it's got to be satisfy both conditions at the same time, A and not B. Okay, so let's say we have A here, but it can be here. But if we look at this one here, we have A, but we've excluded people that are also B. So this is A, but not B. So these are all the people that have cancer, but don't have heart disease, for instance. And how about this ugly one? How about A intersection B? In other words, it could be B, right? B, it's got to satisfy both conditions, B and not A. So it's B and not A. That seems to satisfy that condition. Well, how about this? Not A and not B. Not A and not B. So it can't be A and it can't be B. Oh, wait a second. I'm sorry. I think what they're asking there is, I'm not sure what they're asking there. A? I wonder what the right answer I put down as the right answer for that. Or not A and not B. Well, what's not A? Not A would just be B. And not B would just be, well, actually, be, oh, I'm sorry. Excuse me. Not A, right, would be B, but not including the people that are A, right? That would be this. Not B would be A and excluding the people that are B, right? So that would be this as well. Okay, so I would just count, yeah, I don't know why I could combine that into more than one problem and why that doesn't have anything in there, but I would just stick with it, whatever. I think the answer is that one there, but I'll check that. Yeah, that's a good question. Yeah, I don't know. I think either there's a typo or it disappeared somehow or other, right? But I'll figure that out. Okay, let me see what the, I don't want to give away all the answers but, right now, but when you answer that, you'll see whether or not that this will auto correct. So when you answer that one, you'll see what the correct answer is. I would just stick with this, right? In fact, not intersection of B and not A. B and not A is region 3, right? So that's the same thing as not A, right? Because then it's just people that are B. So I'm not sure why that got in there. So there might have been some other symbol that might have supposed to be in there, but I would just answer the first part there. In other words, that was an attempt to show you that you could phrase it more than one way, I think. And I think somehow or other got lost in the translation there. Okay, so let's look at let's take a look at this while we're here. And then we'll move on to that normal distribution, the binomial distribution. Okay, calculate the prevalence of cooties for this population population based on a random sample in this population. It says a random sample, took 1,200 people from this population, and you figured out, well, you broke it up into this contingency table where you realize that, gee, I'm going to organize this so in the vertical columns that people who have the disease are listed in the vertical columns. People who don't have the disease are listed in the first vertical column. People who don't have the disease are listed in the second vertical column. So that means that the total here in this column represents everybody out of the 1,200 people who have the disease. Turned out to be 150 people. So the prevalence here is going to be 150 out of 1,200. In other words, 15 out of 120, whatever that comes out to be. Okay, so that percentage of people actually have this disease, right? So now we apply a diagnostic test. And in that diagnostic test, we're going to put the people that tested positive in the top row, people tested negative in the bottom row. So the people in this box tested positive and have the disease. That's a true positive. The test worked, right? So the efficiency of this test at identifying people who has the disease, in other words, the sensitivity of this test is 105 out of 150, whatever that percentage is. Right, so let's see, 521 over 21 over 30, whatever that percentage comes out to be, right? But however, we have 45 people that did not that tested negative, even though they had the disease, right? So that would be a false negative, right? Because they tested negative, but they have the disease. That's a false negative test. On the other hand, there were 1,050 people who don't have the disease, and the test got it right 945 times out of those 1,000 people. I'm going to pull up my calculator so we can actually look at the number. So 945 out of 1,050. So it got it right 90% of the time. So the sensitivity of this test, how good is it at predicting people who don't have the disease and testing negative? That's a true negative. It's this box right here. That's 90% of the time it got it right. 10% of the time it got it wrong. And that is a false positive, right? They tested positive, but they don't have the disease. So that's our other 10% of the people here, right? So our next thing that we're usually interested in is how good is this at predicting whether a person has the disease or doesn't have the disease in terms of the result of this test. So if you tested positive in this population, out of 210 positive results, only 105 of them actually had the disease. So a positive test only suggests that there's a 50% chance that you have the disease. So the positive predictive value of this test is 105 over the total of 210 positive tests, which is equal to 50% as a positive predictive value. On the other hand, the negative predictive value, 945 people out of 990 people tested negative, was right for 945 of them. So the negative predictive value is 945 divided by 990 is equal to about a little bit more better than 95% is the negative predictive value of this test. Okay, now one of the things you might get on the test is you might get a situation where let me just calculate what this sensitivity was. It may come up. Sensitivity was 105 divided by 150 is equal to 70%. Okay, that's our sensitivity. Okay, so now one of the things that might come up is that the probability that the prevalence in this population is pretty high, right? Prevalence was, I feel like I should be able to figure it out in my head. Right? Let's see, 300 for 12.5%. 12.5%. It's 150 divided by 1200 is equal to, 1/8, 12.5%, right, is the prevalence in its population. Well, one of the things that may come up in the test is if you redid this for a population with a smaller prevalence, with a lower prevalence, and with exactly the same test, 70% sensitivity, 90% specificity, exactly the same test. If we applied it to a population that has a lower prevalence, so for instance, maybe the prevalence is only, say, uh, let's go to, I don't know, maybe 1%. So 1% of this population, which would be 12 people, right, would be tested, right? 1% of this population actually has the disease. So out of 1,200 people, only 12 people would have the disease. So if it's 70% accurate, right, 70% of 12 people is roughly 9 people. That would be about 9 people testing positive, right? So, and then if it's 90% accurate on the people that don't have the disease, then out of 1,200, this would be 1,188, right? So 10% of those would test wrong. So roughly 120 people would test wrong. So we have 9 people that tested that positive that really have the disease. 120 people that don't have the disease tested positive. So when you add them together, you would get roughly about 129 people, and your positive predictive value would only be 9 out of 129 people actually have the disease when they test positive. So the positive predictive value is only very low. It's only about 10%. You test positive, only 10% chance that you actually have the disease. That's a demonstration that diagnostic tests, the positive predictive values of diagnostic tests, very sensitive to the prevalence. So you may see something like that. We've done that on a class lab video, so I think that you should be in pretty good shape to do that. If you really need to go back and take another look at it, you can skim through it when we discuss diagnostics. Specificity is how good the test is at predicting people that don't have the disease. So in this situation, the prevalence, 150 out of 1,200 people have the disease. 1,050 do not have the disease. So if the specificity of this test is 90%, it means that when we test those people that don't have the disease, 90% of the time we'll get it right. In other words, we'll get a negative test. That's where that 945 comes from. It's 90% of 1,050. We get it wrong. If we get it right 90% of the time, we get it wrong 10% of the time. That's where that 105 comes from. For tested positive, but they're in the column people that don't have the disease. Does that help, Lydia? Does that answer your question? Yeah, I think that would be a decent description, right? I like to describe it a little bit numerically, right? Like this over this, but yeah, that pretty much is what it's saying. Okay, so we've also given you a formula that you can use to calculate if you're given on the exam, if you're given the sensitivity of a test, the specificity of a test, and the prevalence in the population, you can use this Bayes rule, a form of Bayes rule, which is conditional probability, right? Positive predictive value is a conditional probability. If you test positive, what's the probability that you have the disease, right? So in other words, it would be the probability you have the disease given that you've tested positive, right? So disease positive given that you've tested positive. So we can do this with this formula, sensitivity, which is 0.9 times the prevalence, which is 0.1 divided by the sensitivity times the prevalence, the same thing, right? Well, let me go ahead and do this. Oops. Actually, I'm going to use Excel. hear my neighbor outside shoveling my front walkway. So I don't want to get done too soon because I'm hoping to finish it. Actually, he's a very nice guy. So very nice of him to I guess he got up a little early than I did today, or he didn't have anything else to do. Let's see. Let me get the view here. Let me zoom in so you can see this a little better. Okay, so let's go through this. The top part of this equation is pretty simple. It's just the sensitivity, right? Where we sensitivity times the prevalence. So the sensitivity is equal to 0.9 times the prevalence, which we said, if I go back and look, which we said is 10% times 0.1. Okay, and on the bottom, we have to add together two different things. We have to add together the sensitivity times the prevalence, which is the same thing we just did, right? It's equal to the sensitivity times the prevalence, right? And then we're going to add to that, before we do the division, we're going to add to that 1 minus the specificity. Okay, let's think about this. What's the specificity? The specificity here was 80%. It's not the same problem as before, keep that in mind. So 1 minus specificity is 0.2, right? Specificity 80%, so the 1 minus that is 0.2 times 1 minus the prevalence. And the prevalence was 10%. So 1 minus the prevalence is 90%, 4.9. Okay, so that's equal to that. So the positive predictive value is going to be equal to the top of this equation divided by the sum of these two values. Actually, I want to do this. And it comes out to be 33% is the positive predictive value. Okay, so that's how we would use that formula. You could also, if you wanted to, just build a table like we did up here. In other words, say, well, you know, if I start with 1,000 people, the prevalence is 10%. That means 100 of them have the disease, 900 of them don't have the disease. So you have your bottom row there. And if the specificity if the sensitivity is 90%, out of those 100 people, I'm going to get it right for 90 people, get it wrong for 10 people. So you have the first column. And do the same thing with sensitivity. You can build that table, and then you can just add the numbers up across to get your positive predictive value. In fact, you could do that to check your results. It's easy to get this wrong, isn't it? Right. So you could use that to check your results on there as well. Okay. So what's this all about here? The person. Yeah, I guess I gave you some tables to do this, and this is all just basically finding probabilities from a table. And we had a couple of examples like that, I think, in class as well. Okay, so I don't think too many people have a problem with that. Let's take a look at this, the next three homeworks, real quick. Especially, I'm not going to go through the entire homeworks, but I definitely want to do a problem that involves the z-table or the normal distribution, and one that involves the binomial distribution. Okay, there we go. Venn diagrams. Okay, we got that out of the way. What happened there? What happened to two? Oh, I skipped right past this. Let's see. Okay, so what are we having here? Okay, now we're talking our normal distribution. Okay, so question 4. Somebody brought up question 5, right? Which is in this one, this first problem, we're employing the empirical rule, and the empirical rule, as we learned in class, tells us that in a normal distribution, I don't need that anymore, I think. in a normal distribution, a normal distribution is property of the normal distribution is important to us. Oops, wrong end. Is number one, it's a bell-shaped curve. As you get further out from the middle, the frequency of people that this applies to gets lower and lower. This might only be a few percent of the population. The other property it has is that the mean, if it's a perfect normal distribution, the mean is exactly in the center, and the median has the same value as the mean. It's also symmetrical, so we could actually fold it over. So this represents 50% of the distribution. This represents 50% of the distribution. The other thing that we know about it is that there's a certain a combination of properties between the mean. I'm going to call the mean 100 here. What is it here? I'm going to call it 30. Now remember from the beginning how we calculated standard deviation. At this stage, how we got the standard deviation is irrelevant. We know that for this population, the mean is 160 and the standard deviation is 30. You guys know, can you tell me how I know I'm talking, how you should know I'm talking about a population and not a sample? What's the giveaway that I'm working with a population? Any opinions? Oh, actually, it's not. It's actually the fact that I'm using Greek letters. I'm using mu and sigma to represent the mean and the standard deviation. Those are called parameters. When you talk about a population, you call it parameters, and you use Greek letters. A whole bunch of you woke up on that. Yep, use the Greek letters. If we were talking about a sample, I would use X bar for the average, and I would use standard deviation or write out standard deviation for the standard deviation. So this is a population. Okay, so the thing that the other thing the empirical rule tells us, and I'm going to round off here for now. I think your textbook probably is a little bit more definitive, but this is good enough for us, I think. Tells us that 68% of the population in normal distribution is within one standard deviation of the mean, one standard deviation above to one standard deviation below. And it also tells us that 95% of a population is between two standard deviations below the mean and two standard deviations above the mean. Right? So let's see how that applies here. In this case, if I were to ask you for the same population, what's the probability a single observation selected at random from this population would have a value less than 130? Okay, where would 130 be here? The standard deviation is 30, the mean is 160. So 130 would be here, roughly. It'd be one standard deviation, 30, below the mean. So what's the probability would have value less than 30? That's represented by the area below 130, or in other words, below what we call a z-score of -1. We also give the number of standard deviations. We call that the number of z-scores. And that's one standard deviation. That's a z-score of -1 below the mean. So we're looking for this area down here. Well, 68% is this middle area, one standard deviation above to one standard deviation above, below to above, right? So since it's symmetrical, I know that the part that's below the mean here would be 34%, and the part that's between the mean and one standard deviation above is 34%, right? So if this is 34%, and I know the mean, to the left of the mean is 50% of the population, right? It's symmetrical, right? Well, then if this is 34 and the entire half to this side is 50, that leaves only 16% for this area down here. So we can manipulate this empirical formula to help us do this stuff. The person that asked about this was asking about this last one. For the same population, the question 1A, what is the probability of selecting one individual from this population that has a value less than 100 or greater than 120. So 100, right? Where would 100 be? 100, let's look at this. There's a formula I can use. Z is equal to X, the value we're interested in, minus the mean, over the standard deviation, to give us the number of standard deviations it is from the mean. Okay, so we're interested in 100 minus 160 over 30. So that's going to be equal to minus 2, right? 60 over 30 minus 2. So in other words, 100 has a z-score of minus 2. Okay, what about what was the other number we were interested in? Was it let's see, this one's going to be 220. So 220 minus 160 over the standard deviation of 30. That's going to be 60 over 30, or a z-score of plus 2. So it's going to be at this end of the distribution, right? But it's going to be a z-score, number of standard deviations from the mean of plus 2. And we know from our empirical formula that represents 95% of the distribution. So if this area represents 95% of the distribution, well, then that leaves 5% outside of that area. So in other words, the probability that we would choose an individual that has a value less than 100 or greater than 220, in other words, 2 standard deviations below, 2 standard deviations above, would be this area. And this area, the areas that are outside of our 95% for our empirical rule, that leaves 5%. Since this is normal distribution is symmetrical, what does that tell you about what percentage that is and what percentage that area is? We got a volunteer on that? Okay, that would tell you that it's 2.5%, right? I can't tell how long the lag is here. I can't tell you're not answering. It's a lag on the computer. Yeah, 2.5% exactly on each side. So you can manipulate that if you wanted to know the different areas were. Now, unfortunately, we're not always going to be working with situations where it's going to be a nice, clean integer for the number of standard deviations. Let's see. Let's try this one down here. Estimate dietary intake of 10 key ingredients. One of the nutrients was calcium, for adults 16 years, found a mean daily intake of 721. That's our mean, with a standard deviation of 254. Using these values for the mean and standard deviation for a population, compute the probability that a randomly chosen individual over 60 years will have a daily calcium intake under 400 or over 900. Okay, so let's see how we're going to do that. Oops. I got a fresh sheet of paper, virtual paper in here. Okay, so now let's sketch out. I like to sketch them out, even if I think I can do it without doing this. I think I said that was 721. Our mean was equal to 721, and our standard deviation was equal to 254. Let me check that. Okay, let's see. Yep, 254, and we're looking for under. Oh, that's not the question I was looking at. Oops. Use my mouse. Under 400 and over 900. Okay, so let me sketch that on here. So here's 400, and here's 900. We're looking at the percentage of people that are below 400 or over 900. So these are the two areas that we're looking for. So I'm going to start with under 400. What's the z-score for a daily intake of 400? There's a probability I would pick someone that's in this area here, a daily intake of under 400. So z is going to be equal to 400 minus x, which is 721, over 254. Okay, so I'm going to get my calculator out because I suspect this is going to be a nice even number. I'm going to clear. Okay, so 721. Actually, I could just give me a negative number, so I can do it on here. 400 minus 721 is equal to minus 321 divided by 254, okay, is equal to negative 1.26 standard deviations. I'm just going to take the first three digits. I know we can get into a whole debate about rounding and stuff like that, but I'm going to just take the first three digits. The reason why I'm doing that is because I'm going to use a z-table right now to calculate the area that's represented from this value, from a z-score of negative, for a z-score of negative 1.26. Right, that's my z-score. From there down to the left. And I know my table gives me that area directly. So I'm going to go look up my table. I have like using the Gressley table. You can use the one in the book. They're exactly the same table. I just like it's pretty. I don't know why I like it. More comfortable with it, I guess. That's it. I can't find it quickly. There we go. So I'm looking for a z-score of negative 1.26. So there's our z-table. Okay, let me zoom in here a little bit. Okay, so here's our z-table. So a z-score, this is the positive z-table. Notice it says whatever the z-score is, the area you're going to get here is the area to the left. Okay, and this is the positive z-table, which all these z values are to the right of the mean, so it's going to be a bigger area. It's going to be area from here down. So negative 1.2. Now to get the third digit, I have to use the columns here. So 1.2 would be this first, 1.20, right? If it was just 1.2, it would be 11.51% or 0.1151. But to get this that sixth digit, it's going to be 1.20, 1, 2, 3, 4, 5, 6. It's going to be 0.1038. So this area is 0.1038. So a little bit more than 10% of the population, a little bit more than a 10% chance that I might, let me just make sure I got that right. Yeah, I got that right. A little bit more than a 10% chance that I would pick someone from this population that had a daily intake of less than 400. Now I can use Excel to do this also. There's a function in Excel called equals norm s dist. And when I put in parentheses, it's going to ask me for the z-score. And if I put in 1.26, right, and hit enter, I'll get, oops, what did I do wrong there? Anybody know what I did wrong there? Should be pretty straightforward, right? I put in a positive number, right? So it gave me that big value. So if I correct that, put in a negative number, I get basically the same answer that I got here. There's another function that you can use. Equal norm, not norm s, but norm dist. I put in the parentheses. And here I can put in the mean, which in this case was 721, comma, the standard deviation was 254, comma, the x value should have been up front. The x value was 400, comma, 721. And then finally at the end, put in the value for cumulative true, because it's going to give us the area, full area to the left of that value. Okay, and it comes up to basically the same thing. Don't worry about small difference. Okay, so this is because I rounded, right? You remember I used the value 1.26, which is rounded. So it's a little bit different because I rounded there. Okay, so you use either one of them. In this case, norm dist, you don't have to calculate the z-score. If you calculated the z-score already, then this is a little easier to put in because all you have to do is stick in one number again. So that gives us that area. So now what about this area up here? Well, we don't have a z-table or function in Excel that gives us the area from this point up. We do have one that gives you the area from here down. Well, let's see what that would be. Okay, so let's do our calculation here for what the z-score here would be. And again, I could use this norm dist to do that, right? But I'm going to go ahead and calculate it. It's going to be, what was this number anyway? I think it was 900. So I'm going to clear 900 minus 721 the mean, is equal to 179 divided by 254 is equal to a z-score of 0.70. I'm going to round it 0.70. I'm going to stop there because I'm going to use my table. I'm going to go to the table. A positive 0.70. 0.70 is 75.8% of 0.7580. So this area to the left of 900 is going to be what was it again? 7580. 0.7580. Well, what does that leave if this whole area from here all the way down is 0.7580? What does it leave here? Well, it leaves 1 minus 0.7580, or in other words, it leaves 0.2420. Add that, carry 1. Yep, that's right, 0.240. So this area here will be 24.2%, 4.2420. So the question asks, what's the probability that you would choose a random individual that's below 400 or above 900? That's kind of our union, isn't it? The answer either or satisfy the condition. So we're going to add these two together. So it's going to be 0.2420 plus 0.1038. So the probability we would choose someone that's less than this or greater than this is going to be 0.3458, about almost 35%, 0.3458. Okay, you guys okay with that? Comfortable with that? Oh, in this function, it's going to be a little bit clearer when we get to take our last example here, which is going to be the binomial distribution. In this situation, if you say false to cumulative, it's going to give you the probability of being exactly that value. That, like, for instance, if I had said false for 400, it would give you the probability of being exactly 400. Well, the problem is that the probability of being exactly, maybe there's a million people in here, right? There might not even be someone that's exactly 400, right? So it's really kind of describes the probability of that one event happening, right? Or kind of the height of this distribution, kind of more describes what the height is, where this line is, rather than an area. Remember, if you say false, and you're only looking at that specific value, then this is a straight line. It's just a straight line down here. And a line has no area, right? It's just you need width and length to have area, right? This have an area, right? But a straight line has no area. So when you say, if you were to say false in there, it really doesn't give you any information about the probabilities here. Any information that's useful to us about the probabilities here. So for this function, just don't ever bother using false, right? It would be nice if maybe they just left that, but I guess there might be some applications where you might be interested in that, right? But certainly not for anything we're doing. On the other hand, now let's go to our binomial distribution. Things change there quickly, okay? So I'm gonna back out of here. We'll give this a try. Page. That's all. Okay, this last homework, 2C. And I'm going to go back to Excel. Okay. So, yeah, I did a pretty simple example here. Okay, study indicates 4% of American teenagers have tattoos. You have a random sample of 30 teenagers. What's the likelihood that exactly 3 will have a tattoo? A study indicates that 4% of American teenagers have tattoos. Same thing, same population. What's likely to have 3 or fewer? So this one, exactly 3. This one, 3 or fewer. And then this one is likelihood that fewer than 3, and this one is what's the likelihood that 3 or more will have a tattoo. Kind of the same question, but let's take a look at what this means. Now, let's say I were to tell you that 4%. I'm gonna change this problem just a little bit. Let's say I were to tell you. No, actually, I'm going to stick with this, and then I'm going to do a postscript on this. So let's say, okay, so we have 30 teenagers, right? And out of those 30 teenagers, in this first problem, we know that in this population, 0.4, excuse me, 0.4 or 4% of this population has a tattoo. And we want to know what's the probability if I select 30 random teenagers that I'm going to start with one. This is going to be our probability of any individual teenager's 4% chance of going to have a tattoo. Because that's the prevalence, right? Okay, and this is going to be our successes. Okay, and I think maybe they use X or something like that. Let's see. They might use S or they might use that. X doesn't matter, right? Whichever one they use. And in this case, the number of successes is 3. In other words, we're saying what's the likelihood that if I took 30 random teenagers, it's a probability that with a 4% prevalence of tattoos, probability I'll get exactly 3 out of 30 that have tattoos. Well, that's a binomial distribution. In other words, there are only 2 possibilities. Either they have a tattoo or they don't have a tattoo, right? So given that it's 2 possibilities, we can actually work out with this what the probability would be using a function in Excel called the binomial distribution function, binom dist. Now again, you could also use .dist, .dist. It'll come out the same. Okay, I'll use that one for now. Okay, when I hit parentheses, they ask me what's the number of successes it uses S. You forget about the X there. Number of successes is 3, comma, the probability of any individual being having a tattoo is 0.04, comma, and then let's see the number of I missed the number of trials there. Number of trials N is 30. The probability of success is 0.04. See it down here. Number of successes, comma, number of trials 30. Probability is 0.04 any individual person, and then last going to ask for cumulative. In this case, I'm going to say false. The reason why I'm going to say false is because we want to know the probability of exactly 3 people having a tattoo. Not 2, not 1, but exactly 3 out of 30 having a tattoo. Now, this is different than that normal distribution we looked at, where it was just a straight line. This is an actual, it's going to actually a probability. There's a finite number of these people in this group that are going to have that. It's not like I can't predict it. So I'm going to say false. I'm going to enter, and the probability is 8.5%, 8.6%, or 0.086 is the probability that I will get exactly 3 out of 30 that have the tattoo. Well, what's the next one say? What's the likelihood that 3 or fewer will have a tattoo? Well, 3 or fewer equals binom dist. I'll use this one this time, parentheses. The number of trials is still 30. I'm going to take 30 teenagers, randomly selected teenagers. And the probability is the number of trials, excuse me, number of successes is 3. The number of trials is 30. The probability of success is 0.04. And cumulative, I have a choice here, true or false. If I say true, I already know it's just going to give me the probability of exactly 3. If I say false, rather. If I say true, it's going to instead do a cumulative calculation and give me the probability for 3, 2 out of 30, 1 out of 30, and none of the teenagers having a tattoo. It's going to combine all those probabilities together for me. So if I hit enter, the probability that 3 or fewer are going to have a tattoo is going to be about 97%, or 0.969. Okay, so Next thing we ask here, what's the likelihood that fewer than 3 will have a tattoo? Well, first I'm going to answer this one. What's the likelihood? Now I'll answer this one. What's the likelihood that fewer than 3 will have a tattoo? Let me think about that. Equals binomial. Yes, I'm going to type out what I'm thinking. Parentheses. Fewer than 3. So that means 3 is not acceptable. So fewer than 3 would be 2, 1, and 0. So 2, comma, trials is 30, comma, probability is 0.04, comma, and cumulative is going to be true because we want to know the probability for fewer than 3, which includes 2, 1, and 0. So I use 2, 3. So that's 88%. So you see the difference there, right? It doesn't include the probability for 3. The next one asks, what's the likelihood 3 or more will have a tattoo? Well, you want to know something? I just calculated the probability that 2 or less will have a tattoo, right? So 3 or more is all the other possibilities that are left. So in other words, it's got to be equal to 1 minus the probability for 2 or less. Oops, I should have put an equal sign in there. There's 1 minus the probability for 2 or less, which is almost 12%, or 0.1168. Okay? So that's how we would use the binomial distribution. Okay? So there is an outside chance you might see a problem on the test where instead of giving you information about exact probabilities, and well, it could be a little bit more involved. If I were to tell you that, let me start with this. If I were to tell you that 10% of a population is diabetic, 0.10, 10% of a population is diabetic. If I chose 10 people, I'm going to actually, maybe it's an elderly population, I'll make it 25% of the population is diabetic, right? If I were to tell you that, if I were to ask you, what's the, actually, if I were to randomly select 3 people from this population, and I ask you, what's the probability that 1 out of 3 of these people are diabetic? Well, then you would use a binomial distribution. Number of success, the trials is 3, the number of successes is 1, probability of any individual being diabetic is 0.25. That's, you use that function. But on the other hand, if I asked you instead that you take a sample, take 3 people, what's the probability that all of them are diabetic? Well, you wouldn't even need to use the binomial distribution because you know that the probability of first person being diabetic is equal to 0.25. And the probability of the second being diabetic is 0.25. So you just multiply by 0.25 times 0.25 times 0.25. So the probability that all 3 of them are diabetic when you choose them randomly is about 1.5% or 0.015, right? So now let's say that I would actually do this. I go out and I would say, okay, I'm going to take a random sample. How many people in this group are diabetic? Okay, out of the first group of 3 people, I got 2 that were diabetic. Out of the second group that were diabetic, I got 1 that was diabetic. Then I got none. Then I got none. Then I got 1. Then I got none, and so on and so forth. If I did this thousands of times, see, if I did it just whatever this is 6 times, well, I could take the average here, and it's such a small sample that I could just get lucky and find everybody, all of them are zeros, or all of them are 2s, or all of them are 3. Right? Anything could happen here with a small sample. But if I took a really large sample, did this thousands of times, what percentage of the time would I have all 3 of them being diabetic? Right? Well, since the probability of if I take a random sample of 3 people, probability of them being diabetic is 1.5%. I would expect that 1.5% of the time, 1.5% of these results would be all 3 of them being diabetic, 3 out of 3, right? Now, if I told you we did that study and it turned out that it wasn't 1.5%, but it was actually 5%, quite a bit different than 1.5%. What would that tell you about my initial assumption about my random selection here? What would that tell you if it's really different than the result that you would have expected? What do you think that tells you? Yes, this is all recorded. Anyone want to hazard a guess about what that tells you about my assumption about what was my assumption here? My assumption here is that I took a random sample, and implied in that is that the results are independent. In other words, there's no relationship between the first person I sampled, the second person I sampled, and the third person I sampled each time I did it. If that's true, when I repeat it over and over and over again, I would expect to get this percentage of the time to get all 3 of them having diabetes. Right? Well, in fact, if that doesn't occur, that implies that maybe my sample wasn't really random, or the 3 individuals, were not really independent. In other words, maybe if I sampled, only clinics where there were diabetics, well, then obviously I'm not really sampling, doing a random sample and so on and so forth. They're really not independent. If I sample people that were related, like, oh, three people from your family group, 3 people from your family group, well, it's an inherent condition. So it's really not the first person, second person, third person are not 3 different families, same family, then that's not really independent. So that was a big difference here, would suggest that my sample was not independent. Okay, now the only other thing that I think that I think might come up, which might throw you a little bit of a curve, is there is something called the binomial, the normal estimation of the binomial distribution. Okay, and in that, what we're saying is that let's say that we are doing we're taking repeated samples where, for instance, if we're flipping a coin 50 to 100 times, right? We would expect that out of those 100 times that we flip it, that if it's a fair coin, that 50% of the time that we would get 50% of the time that we would get a head or a tail, right? So in effect, if I were to look at this and draw this as a distribution, I can't find my paper. Okay, if I were to draw this as a distribution, what I would expect is that the most common outcome that I would get if I did this, if I flipped 100 coins many, many, many times, and then I drew it as a histogram, or if it's so many times, I can turn it into a normal distribution like this. If the number of coins that I flip, if I flip 100 coins each time, and my probability of getting heads is equal to 0.5, I would expect the most common outcome would be that I would get 50 heads, right? And then occasionally, but on the other hand, very often I would get 49 heads, or 48 heads, or 53 heads, and so on and so forth. But 40 heads is not going to be so common. 30 heads is really not going to be very common. And 20 heads, it's going to be pretty, out of 50, if I flip the coin 100 times, it's going to be really uncommon. Same thing with going above this. So in essence, we can approximate the normal distribution. We can approximate the results for a binomial distribution. We can approximate it as kind of a normal distribution. It's not really a completely normal distribution. It's an approximation to a normal distribution. But a lot of times we can use this functionally. So what I can do here is I can say, well, what is the mean of this distribution? Well, the mean of this distribution is going to be equal to the number of trials times the probability. So what's that in this case? That's going to be 100 coin flips times probability of getting heads is 0.5, which is 50, which is exactly what we would expect. We'd expect that the most likely outcome, the mean outcome, would be 50. Sometimes be less, more heads, sometimes be less heads, and so on and so forth. Well, that's very nice, but this doesn't do me too much good if I only know the mean. What about the standard deviation? If I know the standard deviation, now I can use this to make predictions. So for instance, if I need to know standard deviation, well, you can calculate standard deviation here by saying standard deviation is equal to the square root of the sample size, number of trials, times the probability of the outcome you want, P, times, sometimes they'll write in Q here. Q is really 1 minus P, right? So if you see Q, you can assume it's just 1 minus P. So standard deviation here is going to be square root of 100 times 0.5 times 0.5. Okay, so what is that standard deviation? Let's give this a try. I don't need SPSS, nothing here, no. Oh, yes, yes, no. Okay, yeah, let's do it in here. So it's equal to, let's see, equal to 100 times 0.5 times 0.5 is equal to 25, and the square root of 25, of course, is, where my math go? Here this is 5. So our standard deviation is equal to 5. That's equal to 5. Now, if I were to ask you now, what's the probability that we would get less than 40 heads out of 100 flips? What would that be? Well, gee, I could calculate a z-score for this. I mean, z-score is equal to, now that I know all these values, is 40x minus the mean over the standard deviation. The z-score is equal to 2. So I could go to my, or negative 2. So I could go to my z-table, and I could look up the area that this represents. It's going to be down here, really. 40 is going to be down here, really, right? 40, right? Or negative 2 standard deviation. And I can look up on my z-table this area, because it's 2 standard deviations below the mean. I know that this, even without going to the table, I know that this is going to be roughly 2.5%, or about 0.25, right? You can use the z-table. You can actually go to the z-table, look it up if you want. But I know that it's going to be around that amount. So I can use this normal approximation to the binomial distribution in lieu of using my real calculator. In Excel, this is an approximation. This actually gives you, the normal distribution. This particular function, the binomial disk function, actually gives you a real calculation of the number of possibilities that satisfy what you're talking about over the total number of possibilities. Gives you a real probability, right? Real accurate probability. This one gives you an approximation. So if it comes up on the test and you're told that you have this situation, you're given this, and you have to use the normal approximation to the binomial distribution, you could do this. I think Dr. Waldron brought this up briefly in a lecture, so I just want, in case it comes up on the test, I just want to be a little bit prepared for it. But I think it's pretty simple, I think. So I don't think you'll have too much of a problem with it if it does come up. And if it does, to make a few notes here about this. Remember, it's open book, so you'll be able to go back and look at all of his PowerPoints from his lectures, any of your notes, and so on and so forth. You're not going to be able to play back my videos. I guess you could if you really wanted to. I mean, it might be a little time consuming, and you'd have to know where to look so you don't kill a lot of time. But if you're going to do that, I would bring some earbuds, something like that. So obviously, we can't have everybody playing back my voice or the lecture, Dr. Waldron's voice is on the lecture. And we no longer access 5.1. In regard to assignment 1, you no longer, you can access it. Well, make sure you can't access it. You say, I'll grade what the addition. I'll grade the additional. What happens is because there's documents you have to upload, it will not auto grade. I have to go in there and manually grade it, right? So I will today and tomorrow morning. I'll go over all of those and give you some feedback on it, okay? So in fact, maybe even for that one, I might actually post the answers. I normally don't post, even though I go over them here, so you kind of see me working them out. You see the answers in the videos. I normally don't post just the answers because I want to encourage you to keep going back and trying them, and not just slug in the answers. Okay, so guys, I think that's about it for today.